That's really like something. Yeah. It's the last question when you do stuff. Stay with them. All
right, take good notes. I'm going to start from the beginning because it's hard to start halfway through a proof. So this one is that there actually exists a positive real number x. Yeah, square root. I'm just going to start from the beginning because it's hard. Like we had a weekend too between. So bizarre as it may seem, you're used to the square root of 2 symbol, and because of that, you you think of that as, you know, what the expansion is, 1.14 dot dot dot. You think of it like that, but actually, just knowing it exists, somebody made up that symbol with the radical and the square root of 2 to represent that point. How do you know it actually even exists at all? So that's what this is about. How do you prove that this value where you have the solution to x squared equals 2 exists in the real numbers? And I mentioned also I for the complex numbers. You think of I as I squared is minus 1. That's because if you take the real numbers, actually it's the rationals. If you take the rationals and say, I'm looking at x squared plus 1 equals 0, that polynomial has coefficients that belong to the rational numbers, but it has no solution in the rational numbers. And so you ask yourself, like, what would I have to, well, let me just extend. Let me extend my space so that it includes this arbitrary root that I don't know, you know, that's why they called it imaginary, but it's not imaginary. It's like the symbol that represents the solution, x squared plus 1 is equal to 0 is I. And then I'm going to assume that I'm just going to make that symbol. I have to prove it exists. And then I have to look at all the properties that have to be in place to make everything nice. And if you do that, you extend that so that you get that I included, you get the complex plane. So that's what that is. It's easier to think about it in I because you're less familiar with it. So my overarching strategy is to use soup So from your sheets, you guys were definitely confused with this set notation back at the beginning. It seems so boring at the beginning, but the members of this set are real numbers with the constraint that when you square them, you're going to be less than 2. So the stuff after the colon is the constraint. The members of the set are the letters S that belong to reals. So that was confusing for you on, I think some of you had like 2 is the soup here for a set like this. It's not. It's that's the notation square root of 2, which we don't know exists yet. So I broke this down into steps, and I'm going to have you fill in one step. So it's almost a copy paste of what I'm doing, but with soup and turned around. So watch carefully and ask questions so that I know that you got it. First step is to apply the soup property to S. S is that set. Again, I'm just going to rewrite it. It's on your pages. You don't have to rewrite it. It's the non-negative real numbers such that S squared is less than 2. Is this set bounded? Well, first of all, is S non-empty? Whoops, wrote off the page. So that's true. This is my attention to detail. I used to always forget to show the set is non-empty. So I'd have beautiful proof. And then one of the other grad students would take it and say, I found a mistake. What's the mistake? You forgot to show the set was non-empty. I took my rage out on them. Like the worst thing. You spend hours and hours writing up homework and you're about to turn it in and someone looks at it and says, you forgot to show your set is non-empty.
They tag it on in here.
A stab in the eye was much more satisfying. The proofs get longer, by the way, as we go into grad school. So, you know, when you have like 10 pages in your proof and then someone takes it and looks it over carefully and says, you forgot to show the set is not non-empty. You're not going to feel like putting arrows and saying, I trust me, it's non-empty. You're going to feel like, so is it bounded above? You can choose anything. You could choose 100 if you want to show this is bounded above. You just need a real number that's bigger than anything in this set. You guys chose, I think, 2. It doesn't satisfy the constraint. So there's a number that doesn't satisfy the constraint and it's above everything else. I'll go back here and put my check mark here. In real analysis, this is for each of these areas, you kind of saw a method of proof. I think the beginning of number theory, which gets hard really fast, but the beginning of number theory, you just had to write down the definitions and stuff kind of flowed out. I gave you some hard problems, I think, in number theory, actually, with the Mersenne primes. You had to pull things. Combinatorics, you were always kind of trying to organize everything. So there's like a method or a way of thinking. With the real analysis ones, you always have to have a candidate. So if you have to show a limit exists, you need a candidate for that limit. So things like the soup and the inf give you that candidate. Once you have that candidate, you go about trying to prove that that actually does what the job is supposed to do. So now my candidate is the soup of the set, and now I'm going to show it indeed satisfies the equation and therefore it exists. So let me actually fill this in for you beforehand, so it's not just this stuff here. So the trick is to show that it's not going to be bigger than 2 and it's not going to be less than 2, but it's a real number. So x squared has to equal 2. So this is the strategy. So I'm going to do the one where x squared is less than 2, and I'm going to ask you to do the one where x squared is bigger than 2. It's not hard. It's not bad. It's good stuff. Pre-calc or maybe algebra. High school algebra, not the algebra that Isaac took. He had it from a very good teacher, though.
Yeah.
I had someone miss the first week of class for algebra, abstract algebra. He said, I know algebra. So he took an extended vacation. And then he came in, he's like, what is going on in here? Okay, so how do we do this? So step two is this step 2 or 3? So step 2, assume on the contrary that x squared is bigger than 2. So for your side, you're going to assume on the contrary that x squared is less than 2. So you're going to almost imitate what I'm doing. Math talk, right? Observe that. I was helping my youngest sister in proofwriting for geometry. And I'd say things like, let O be the origin. She's like, we don't let O be anything. I've never seen my teacher do that. I'm like, you can call it anything you want. Why can't you do that? And she's like, no, he never does it like that. Math talk. Okay, so if I take a natural number, then 1 over n squared is less than 1 over n. True, right? 1/4 is less than 1/2. 1/9 is less than 1/3. So if I make the bottom larger, it's going to be smaller. And you kind of thought those things through in calculus, right? When you took limits. So, and I think I ran through this inequality. X plus 1 over n. By the way, FOIL's not a thing. It's actually the distributive law that gives you FOIL. Back when you first learned algebra, I guess it depends on the teacher, but when you first learned algebra, they probably showed you distributive law and that you get square this times that, double square that as your thing. If you didn't have like that kind of a teacher and they just showed you rules, they just probably said FOIL and that was the end of it. But it's the distributive law that allows you to do this, which is really, really important in abstract algebra. And then this, I'm going to cap it above. Again, this is a trick that you see a lot in real analysis. You'll see, I want something to look nice. I have to just show inequalities. So I wish that 1 over n squared was not 1 over n squared. I wish it was a 1 over n, but because 1 over n is bigger than 1 over n squared, I can make an inequality. So that holds. And then you get this is equal to x squared plus 1 over n times 2x plus 1, again from the distributive law. Let's see, write this a little neater. Well, x is a fixed number. It's some real number that's inside. It's just a real number. So it's a fixed thing. So what happens if I jack up n? That one will deflate to 0. So I can make that term, that 2x plus 1, I can make it small because I can just jack up n. So that's what I'm going to do. I'm going to choose n large enough. This guy here is bigger than 0 because 2 minus x squared is bigger than 0. Let me do a little bit more math here. Because what allows me to do that is just what you just said. If this is a big number bigger than 0, this is a number bigger than 0, but I can just jack up the n so that this number becomes small on this side. So eventually, this is going to be such a small fraction that it's going to be smaller than this side. Agree? You wait? Stay with me because I'm going to ask you to do it on the boards with the reverse direction. And I'm going to ask you why on each point. So does everybody understand so far? All right, here's my contradiction. So if I let cap n be the n that worked, then what I have here is x plus 1 over n squared where I started is less than or equal to x squared plus 1 over n times this little piece, which is less than x squared plus 2 minus x squared, because I just did that. Oh, it's so fun when you have x squared and minus x squared. You can just cross those out. And you get that this is less than 2, or it's actually equal to 2. So what that means is x plus 1 over n is in my set. It belongs to the set. Right? Because when I squared it, I got something less than 2. That's a problem. Because I've just added something to my soup and it's inside the set. So what's happened is here's your set blob down here on the real line. And then I have this x, which was supposed to be higher than all of it. But then I added something more to the x and I got something inside the set. That can't happen, right? By definition of soup, anything added to it is supposed to be bigger. Tracking, Isaac? Bridget, make sense? So I don't have this as a sheet, but here's what I want you to do. So I want you to repeat this whole thing. You're going to do the same trick. Expand that. And then next, choose n so large.
You did assume on contrary that x goes greater than 2.
No, I did x squared is less than 2. I can easily do those kind of things, but not this time. This is going to give you your contradiction because what that says is that you have the soup. I subtracted something for the soup, so I dropped it inside to this. It's supposed to be inside the set. That's the alternative definition of soup. But it ended up being an upper bound. That's impossible. So this is how you're going to get your contradiction. So go to boards.
6 and 7.
Yes. You can nearly copy and paste what I did, but you're going to do it for instead of x plus n 1 over n, you're going to do these calculations for x minus 1 over n.
No, when you're going through the screen where you just told us what to do.
Yeah, I'm waiting
Oh,
for it.
Yeah.
That's right.